Again. Hi, everyone. I guess we're going to get started here today. Welcome to another Haskell study group. I'm Ram Vaden with Atlanta Functional Programming. Today, we're going to hopefully finish up our discussion on the applicative type class. Last couple of weeks, we've been covering this type class, and it's fairly involved. Remember that this type class is basically representing what could easily be described as a monoidal functor. That is something that could preserve the structure and identity and the compositional properties of a functor, but at the same time, the operations itself can also be associative. Last week, we kind of covered the applicative laws, and I kind of went through my bit of understanding on how these laws are kind of represented, and a little bit of a thought with some examples on how to actually play around with them in the REPL, so you can get a good understanding of them too as well. We'll continue to do that a little bit today, but in addition to that, we're going to also add some quick check properties in our code to kind of like make sure that we can preserve these properties, because as I think I've mentioned before, and I'm going to keep mentioning throughout these discussions on the various type classes, whether it be monoids, semigroups, functors, applicatives, or monads, these type algebras, while their type classes are available and the instances are available inside Haskell, the Haskell compiler itself does not formally type check your instance as being closed under these operations, and therefore it is of this type. It only knows that you're defining an applicative instance for your type. And if you define the instance, the type class instance, or if it's a built-in, it'll go and look up whether or not a built-in type class instance is available. But it doesn't actually go and check to make sure that that specific implementation is correct, and in that it preserves the properties of each of the individual functions and what their properties are supposed to uphold. We've already kind of talked about this in the case of, say, functor. If you guys need more information on how that piece works out and some understanding on how that might be related to what we're talking about today, by all means, go ahead and look at our older episodes on the functor type class that we've gone through and talked about and discussed. Today, I'm just going to specifically focus on applicatives, just merely because I want to kind of finish up some of the specific pieces of discussion on this type class, get some formal checks in place so that we can actually try out an exercise that I saw in the book. And hopefully if there are any additional questions related to type classes that we've covered thus far, I can answer them to the best of my ability. So without further ado, a reminder of what the applicative laws are, all right? As I'm showing you right here, basically, the applicative laws include identity, composition, homomorphism, and interchange. And if you recall, identity is being, obviously fairly simple here. Basically, if you take a pure of ID and apply it to some value v, you get the original value back. Now, pure, remember, is actually taking the function ID and lifting it into the actual functorial structure represented by the value v, right, in this case. So an example of this, if we go back to, say, our REPL here, is if we call pure and on ID and apply it to, say, a list. Okay. In this case, what this is happening is pure gets lifted into a list itself, and then that's actually being applied to each of the individual elements inside that list of 1 through 5, and we get 1 through 5 back. So this is kind of
Ron,
equivalent. Yes.
I don't see. I see your initial, but I don't see your screen.
Oh, 1 second. Do I?
I'm seeing your screen.
Oh, really? Okay, so it's my problem. Okay.
Okay.
What do I do?
All right. So this is this pure ID applied to the list is equivalent to what we see here. This is functionally equivalent, no pun intended. And this pure operator, though, can be used, and this identity can be used in any type class, any type that has an applicative type class instance defined on it. So, for example, for the built-in types that are already available in the prelude, this includes calling ID on, say, the maybe type, all right, which includes just or nothing. And you can see here that this will just work as is, and this actually works through and includes, say, for example, the nothing class too as well, right? And it also deals with either and which is left or right, and the either type also includes, say, if we do left 1 and or if we do pure ID right 1. At the end of the day, this is actually going to be the appropriate either type for each of these. And you can see that here when we just look at what's actually happening here. It's taking a number and then it's returning either A or B. The next property that we kind of covered is actually composition. Composition is fairly straightforward. I think it's pretty simple for us to actually go through and just talk through the idea, but simply put, composition is essentially doing nothing more than, again, lifting the functions that you are trying to apply and making sure that those get appropriately, actually specifically, it's going to lift and the composition operator into the functorial space, and then compose UV and before applying it into W, and you'll see that this is the same as if we have U applied to some functorial structure where V is applied to W. And the reason why that is because, remember, we are the functorial structure and functions in general, when you're dealing with it in Haskell, is they are right to left applied. All right, so that means the rightmost function is applied first, and then it goes out towards the leftmost function. All right, so that result is actually passed into the next function, and so on. We'll see an example of this when we go through and write the quick check properties, but I'm just briefly, reiterating some of these properties for those who are, following along here. You could see has a quick example of this is just nothing more than if we do, for example, a +1 here, and then we do apply this to, say, a +2. Okay, that is applied to, say, a list of 1, 2, and 3. All right. In this example here, what's going to happen is we're going to essentially call +2 on each one of them, and then we'll call +1, and then you'll see that this is going to start with 3, 4, and 5, and then it's going to become 6, 7, and 8. And is 3, 4, and 5, and then 4, 5, and 6. Sorry. So this is if you just call this as is. But another way of doing this is simply just doing the following, which is, since we have that list operation, instead of making these simple lists like this, you can also do, say, pure, take the composition operator, apply it on, say, the list +1, right? And then apply it on the list +2, and then we can just apply that on the values 1, 2, and 3, and we'll get the same functionality. And again, as before, it doesn't have to necessarily be just lists here. We can, just say we have just one, and then let's say that we just wrap all these into a maybe type, and this also works in the same case, right? Homomorphism is another one that we talked about last time, but the idea of a homomorphism, is a common thing in algebraic structures. Category theory kind of picked this up as a generalization of the abstract algebra or modern algebra concept, at least as I understand it. And basically, the idea is you are taking a function and you're lifting it up, all right? And you're taking a value and you're also lifting it up. And that's the same as if you have lifted the function applied to the value prior to actually lifting it into the functorial space, okay? So an example of this is let's say that we have just pure, all right? And we have a +1, and we apply it to a value 1, okay? This is the same as if we've actually, and again, this is in, the idea is stems from our discussion on the applicative laws, which for folks following along in the book, this is in 17.5, this example, which I thought was pretty interesting, because what's specifically this is showing you is we can either apply the function to the value directly and then lift it up, which in this case, when we do a t, we're actually just taking a function, okay, that's going to be treated as an applicative and a numeric value, and then we're just applying it to f of a. And in this case, f is any applicative. It doesn't have to be a known applicative, right? The Haskell compiler in this case is actually just determining whether or not there is an applicative defined on, I think it's on the function operator itself. Which one would be applied on? It would be the it's just going to be any yeah, here we go. It's going to apply the function on operator that is restricted on a particular type here. And then that's what's constructing ultimately, that's what's lifting this case here to the applicative space, okay? You don't necessarily need to do this, obviously, because the result of this has the same as if you called the increment function on the value itself. There is the structure that the pure operator is actually returning is not one that we need to worry about in this particular case preserving the laws. All right. But the reason why this homomorphism law exists is because this lifting aspect of preserving this functorial structure, all right, is what gives the applicative its monoidal properties, right? This allows you to actually lift anything and actually preserve the associativity of the function application, okay? But it's not talking about structure preservation here, okay? Structure preservation comes from the other properties. This is mainly about lifting this guy into some sort of space to apply different functions to different values, okay? Does that make sense to folks? This is at least as I understand it, and I'd be more than happy for folks who disagree to write comments on the YouTube channel, or the live stream, or folks who are in our Jitsi meetup discussion. For members who of the Atlanta Functional Programming meetup who are watching the live stream, we are having a Jitsi discussion of this. Feel free to join us here as well. This is at least has how I understand the homomorphism property. The final thing is, again, this one was a pretty weird one that most people, and at least when I looked at it, it took me a minute to actually go and figure out. But the idea is interchange. The interchange property is the idea that when you apply your functions, which is on the left hand side, this u, okay, to a value that has been lifted, okay, this is the same as if you took, say, the function, which is that has been the dollar operator function specifically. And remember, the dollar operator is a convenience operator to get rid of parentheses. Specialize it on the value, okay, lift it up into the functorial structure that's defined by you, and then call this function. Because remember what the dollar operator represents. The dollar operator represents, if you're doing, let's say, +1 of +2 of 1, which will give us 4. You can also write this as $1, and it's essentially the same. It's essentially the equivalent. Or you can even get rid of this dollar and just do that too as well. And you have one function application. So this is implicitly composing these two functions and then applying it to this one value. And what this interchange property is doing is basically saying right to left function application is still preserved if you specialize on the right hand side of the dollar operator, and then use that as part of your functorial application when you call the star operator from the applicative. That allows you to essentially use either or, whether you need to specialize on a specific set of values and then pass that into a series of functions, or whether if you have a series of functions and you want to specialize value, both sides of the equation are equivalent. Okay, so just to give another example of this is if we say excuse me, $2, and we try to apply this on, say, the maybe type +2, this is going to give us +4. And this is the same as if we just went ahead and took s +2 and applied it on pure 4. Sorry, pure 2. All right. So it's the same. It's the same idea. Both sides actually were equivalent. Are equivalent. In one case, in the left-hand case, in this case specifically, we are lifting the values into the same functorial space as the left-hand side. In the other case here, we are lifting the left-hand side, that is the functions that we want to apply, to up first before applying it to the just on +2. All right, so both of them are equivalent. Now that we have this kind of thing, obviously we want to be able to make sure that whatever we write, all right, actually are correctly preserving these properties, right? So we're going to write some quick check code here just so that we can test these laws. Now, before I do this, I thought it would be useful once we set these laws up to go back and look through. I think it was the maybe applicative. Yeah, we haven't actually covered the maybe applicative, and essentially check to make sure that we are understanding how the applicative is done for some of the built-in types. In this particular example, though, when we are building up our properties for the quick check properties for the applicative, we're going to end up coming up with an example of something that would fail, and obviously, make sure that we are correcting it accordingly. All right. Let's see here. Since the applicative, we've already written examples of properties that are available with the functor type class. The book actually gives a very nice library called checkers that we can use that has these properties already available for applicative, and we're just going to go ahead and leverage this. I think this is a very useful library. To do that, obviously, we need to fire up our Vim on Cabal, go into build/depends, add, I think it's called checkers again, and we do stat REPL. It's going to go ahead and install it for us by, again, downloading it from the internet. Once we get all the dependencies, we'll be able to actually then leverage this. While this is installing, we can actually go in and then play around with writing out some code. So in here, we have our applicative overview module. We're going to go ahead and import data.monoid. Okay, data.monoid is already available. It's in the prelude. We're going to import quickcheck because we're going to obviously use this to verify our code. We're going to also add the checkers class, which is necessary to actually go in and get those properties that we're going to be discussed, that we're going to leverage. We're also going to go ahead and use something called classes, which will be required for some of the equal checks that we're going to end up leveraging. So now this example is somewhat similar to what the book called the bull example. Let's say that you have some type called foo bar, where we either have foo or bar, okay, deriving from EQ and show. So because this is necessary so that we can actually get some very nice, display in our REPL. And then what we'll do is we're going to define, so arbitrary is a type class instance that is available from I think arbitrary, was that the one that's the one that was defined in the book? I think so. This is the one that was defined in the book. One second, just looking through my notes here just to make sure that I have this set up. Oh, no. Arbitrary is inside quickcheck. That's a different thing. Okay, so what we're going to do is we're going to define arbitrary, which is on foobar, because we're going to be generating some code with this. All right, so here arbitrary is the function that we're going to call. All right, that will determine whether or not what our distribution is. Okay, this is going to generate essentially some random value from our sum type. Right now, since we have only two sum types, we could just simply do this, and then you'll see later on why this is going to be problematic for us. All right. Obviously, I need to make sure I get notation correctly. Otherwise, we'll end up having some problems compiling this guy. Once we have this generator already defined for us, and let me go ahead and load this guy, applicative overview. Okay, and let's define now our monoid for this class. All right. On foobar where, and let's, for the sake of example, we define an empty to be foo, so we're making that our identity, and we go ahead and run regardless, and we just return foo all the time. All right. Again, this is mainly just to show you the properties that are available in this checkers library. Okay. The checkers library has something called the equal property. All right. This is a type class that allows you to specify what your equality operator is going to be. Okay. And it's going to use this to actually go in and test your code, but we need to define this on our foobar. So EQ, okay, on foobar, where again this operator is equal to EQ, and again we'll just go ahead and do that. Once we have this, we're going to write a quick main function here. This main function, again, if you're writing it in a file, remember to specify that it's going to return the IO monad. And it's going to basically call quick batch, which is part of the quick check library, to run a series of tests against this monoid bar. All right, monoid is defined in data.monoid. All right. We're right now using monoid for this case, not applicative, okay? And the reason is because this is just an illustration of what is already available in this library. It defines checkers for monoid, applicative, monad. I think it applies also for functor. So you don't necessarily need to do what we did last time and define them yourselves. In the functor class. I did not realize that until I read this chapter, I didn't realize that this library existed. So for folks who have been following along, started, writing some of them manually, it is unnecessary because this function, this library exists. Now, the EQ piece in this code, this is part of also the checkers library too as well. Checkers actually exports a function called EQ that defines or is redefining the existing EQ or looking up the existing EQ instance for the given data type. So if you have an equality operator defined for a given data type, EQ will work for that data type automatically. Which in our case, because we're deriving from EQ, it's going to go ahead and just use whatever the derived generated EQ is from the Haskell compiler. Right.
Okay, I have a question.
Sure, what's up?
So you have on your instance monoid foobar where you have m empty equals foo, and then m append anything equals foo, right? And then now down on line 79, it says main equals quick batch on monoid bar.
Yes.
So why do we use bar rather than
You're going to see. You're going to see. You're jumping
okay,
ahead.
all
right. You're jumping ahead, man. Why are you jumping ahead? Yeah, so we're going to reload this guy. Oops, did I? I may have updated something wrong. Hold on. No instance derived from SemiGroup. Okay, 1 second. We need to actually define. Oh, right. We need to also define SemiGroup for this now, don't we? Didn't believe we should be able to. We needed to define SemiGroup for this, but let's see here. What is going on? Let's see. Did I mess anything up here? This might be something. Instance, no. Instance for SemiGroup arising from instance declaration. Let me just make sure that sometimes if I'm defining this incorrectly, it's going to, the indentation probably messes things up, but we'll see. Okay, so it really is looking for a SemiGroup instance. Okay, that's fine. Let's go and remind ourselves what SemiGroup this definition is. I have to. Okay, we defined this before. Let me just pull up our functor side overview here. And making sure that I get the SemiGroup stuff correctly. Oh, wait, not functor. Monoids and SemiGroups. There we go. SemiGroup. Okay. Okay. I have to get this guy. Okay. Let's go ahead and for the time being, let's go and define SemiGroup on foobar where, and we're going to just go ahead and say, for the sake of associativity, we're going to always return. Let's make sure that I get this right. I think I just need to return Yeah, I just need to return one or the other here. Okay, good. So we'll always just return foo here, just for the sake of example. All right. Now let's go and load this guy again. Okay, so now everything is loaded. Let's run it. Immediately, you're going to see a couple of things here. One is the associativity, M-append, and MOK is all great, but we fail on identity. Why are we failing on identity? Remember what identity defines, right? It's whether I times X or X times I, which is representing left and right identity. This all needs to be equal to X. So if we're passing bar in this case, which we are, we should actually go and return bar. So we need to actually go and fix that. MMT clearly needs to go and change how we need to set this up. Okay. I'm going to leave this piece as an exercise just because this one, I think it's a pretty straightforward fix to actually go and fix it. I think it's a matter of just actually verifying MMT here, which again, MMT, if you guys don't remember from monoids here, MMT takes in anything and just returns an A. And you just need to make sure that when you define, I think you could just go ahead and say MMT is equal to ID, and this will just work, right? And that's and then we need to obviously fix M-append here for left identity and right identity. I think it's no, maybe not so straightforward. Let's see. I think it's okay. Hold on a second. Let me pull up the example since we've done this before. And I'm just messing it up right now. Okay, so we need to figure out what our identity is. We're just going to call it that. And let's go ahead and mess this up here. Foo and bar, we'll just go ahead and define this usually. Foo and this. We're going to go ahead and define it the same way that we defined our Boolean class here a little bit, just to kind of see what is going on. And in this case, we're not we're using the SemiGroup stuff as is, but we could do. We're not actually restricting the second type on our foobar class because it's unnecessary. Boolean can be anything, but here we're just going to go and try this. Yeah, oops, sorry. Foo is foo, and then let's just say bar and bar equals bar, and let's just go ahead and define this as being that, just like we did before. All right, so let's see if that fixes what we just did. There are some fixed there. All right, I need to go and remind myself how to set this up for left identity, right identity in terms of foobar. but I will. The purpose of this discussion is not to debug the monoidal test. It's just to make sure this specific example was nothing more than to verify that checkers was properly installed. Quick batch is what's actually generating a series of tests for us, and then calling out to arbitrary, which will then return one or the other of a frequency distribution. But if we want to, like, say, test a let's say an existing applicative, right? It's like the list applicative. It's going to be a bit difficult because you're going to have to verify. We're going to have to first define a test batch to actually go and handle the applicative instances themselves. That test batch is going to be a function, but the type constraints on the function are going to be really, really complex. The main reason for it is to make sure that some of these properties on specifically the applicative itself that you're using, or in this case, anything that can be treated as a lift type constructor, can actually be used to generate arbitrary instances. All right. So I'm going to show an example of this. This is something that the book actually defined for test batch, but I think I can actually go and show this to you. I think this is already defined inside checkers. So let me just go look this up. Yeah. So checkers provides this applicative function, just like monoid that we see it before, okay, and functor, okay. These are all specific test batches that you can leverage, and the applicative one is particularly complex because it requires how to manage the particular, how the applicative M is related to the types A and B for the given generation function that's going to be created by test batch. All right. Some of these we've already talked about, particularly are the arbitrary type classes, part of the checkers library related to how to generate distributions for that particular type. Co-arbitrary is clearly the complement for arbitrary for generation for the data. The one thing to note here is the show function and how the show type class must be defined. This is necessary specifically because when we run quick batch against any sort of test set, all right, we need to be able to show what the input is and what the output is. And for that, you need to have some ability to actually go and display the inputs and outputs, which is why the show is necessary for applicatives. Notice that it's defined for, actually it's also defined for all three. So any of these require, whether it's monoids, functors, or applicatives, it requires that the show is defined for that particular user-defined type or functorial type, or in this case, applicative type. Well, the applicative type restricted on the type that you are defining. Let me be very specific about that rather than so when you define your user-defined type, that needs to be showable. Then when you define the applicative restricted on that type, that needs to be showable. Deriving show makes things easy. Sometimes you may not be able to derive show, but in that case, it's you can decide how you want to return the string for the show type class, which I think we've talked about at some point. But basically, it's the implementation of show or show precision, and it's going to return some sort of string, right? So let's go back to this. How can we use this? Well, let's take an example. Let's simply take a list of a tuple, right? 1, 2, and 3. Okay, and it's a homogeneous tuple, right? The tuple is each member of that tuple that triples in this case is of the same type. Okay, given this homogeneous tuple, you can call quick batch on applicative of x's. Again, remember this the $sign is getting rid of the parentheses, and when we do it, you can see that it will actually verify identity, composition, homomorphism, and interchange for us. All right. It's going to try a lot of these tests, and it'll take a little bit of time, but it actually includes not just the applicative properties. It actually will run the functorial test too as well. So the functor tests and the applicative properties are all tested with this applicative test, because again, an applicative must be a valid functor. All right. So not all functors are applicatives, but all applicatives are functors. Okay. Keep that in mind. So when you're running these tests and when you're trying these tests out, make sure that you are maintaining the functor properties of your applicative. All right. That's the other thing I wanted to talk about. Actually, you know what? That's really the only remaining thing I wanted to actually discuss here for this one. I mean, of course, we could talk about zip lists, but I'd really, I encourage you, for folks, now that I kind of understood these properties, I think those who are following along in the book, please read and try and see if you could prove or set up and use the zip list monoid example that's in the book, because that's actually something that I'm going to leave as a mystery for those of you who don't have the book, so you guys can go grab it. The book is really, really awesome. These authors actually have done a great job with it. Let's go back to the maybe concept here, because we saw this actually work on actually, let me pause here and see, for those who are following along, if there are any questions. I know some who are following along. If you guys are just starting your Haskell journey, my apologies. We've actually have been running this for quite some time now, and this type class stuff may be new to all of you, but the essence of algebra, type algebras, and the essence of really Haskell's definitions boils down to not just these predefined type classes. Okay, remember, at the simplest form, every algebra that's available in Haskell is a type class that you need to define instances on your given user-defined type. All right, think of the type class as an interface. All right, and each of these functions, all right, or these properties are going to be some sort of function that you have to define for your type on that interface. All right, so you're implementing that applicative interface, if you really want to talk about it that way. All right, but it's much more than that, because it's not just an interface. It's not just you defining these functions. You should actually go again and run quickcheck and make sure that your definitions adhere to the actual properties themselves and what they expect, because then your type class instance is appropriately closed under those operations, which means implicitly you are a valid instance of this particular type class, which means you're valid algebra. You're closed under that particular algebra, whether it be the applicative algebra, the monoidal algebra, the semigroup algebra, the functorial algebra, and so on. All right. Let's see if I can actually grab this last thing that I want to kind of discuss, and then I will open the floor to any questions at all. This is going to be okay. So for the list applicative, let me just set this up here. Make sure, because in order for us to go and explore some of these things, we need to have this turned on. Now we can actually go and say T, let's say this for our test, and do that. See that it's a list of A, and it returns an A. Now let's say that we see type applications on, make sure pure at this. Yes, it'll take an A and return. Okay, good. So it will lift. So this is a good illustration that I should, for folks who may have gotten confused of my use of ID earlier. On pure and show identity. Or even, I think a better example would be the homomorphism. Remember our homomorphism example here. If we end up calling pure T pure plus 1 applied on pure 1, what is the type? You can see the type here is nothing more than the type is the applicative type is irrelevant here. That's what that means right there, that we saw earlier, and this is essentially the same idea. Talk about the list applicative. Where's the maybe applicative notes? Oh yeah, one particular type that we did not talk about that was mentioned in the book, or actually we kind of talked about but wasn't entirely, it was get constant. So the constant, we've talked about constant versus constant in prior, I think in our discussion of functors. So just be aware that you can actually define, when you're defining your constants, you can define an applicative for that constant. Again, that's an interesting exercise to actually go and try yourselves to see how to actually go and set that up. Because remember, the thing about constants is that they are read-only, right? So you don't want any sort of application to actually really go and mess with the constants themselves. The maybe applicative is kind of a similar idea. So if we look at the type maybe, okay, it's the kind of maybe. Remember that this is just a single kind of type, which means we can actually have description of it. And remember, maybe is just either nothing or just, right? So when you're defining the application of the maybe type, and you're trying to define or use the maybe applicative, specifically in this case, since it's actually defined on it, the one thing to recognize is the fact that nothing literally will return nothing. And so when you are doing monoidal applications and at any point in time you have a nothing returned, um, you will automatically cancel out all the rest of the operations that you do, even if you have maybe a applicative, just because if you're using nothing for the maybe and you're applying a series of functions, it doesn't matter what you're going to pass into the function, it's just going to return nothing. Let's show in this case how, say, for example, if we do just +1 apply to just 1 to kind of show what this maybe applicative looks like. So again, in this case, it's just going to take a numeric b and convert it and lift it. And actually, you don't even have to do that. We can actually do pure 1, because here we're going to lift the 1 into maybe before actually applying the function. All right, this goes back to what we were talking about before, which is the homomorphism application actually is preserved. All right, it'll lift whatever side of is necessary. All right, so if you decide you have data like this and you just have a series of functions, you could just literally do this and suddenly everything will just become an applicative, and there'll be a functorial structure of the same type. All right. The advantage of this pure really is something that we will end up encountering in many other very practical use cases. Think one very specific thing that comes into mind when I looked at this is data transformations. If you are, say, using a database library of some sort, and the database result set is written in such a way that it could be F mapped over, all right? As long as the operations are associative, you could theoretically also define an applicative instance on that result set. And then now you can write a query, get the result set, apply a series of transformations against it. And you don't necessarily need to know the structure of the result set, because you know that your pure operator will just lift those transformations into the realm of that result set definition as it's defined for your applicative type, and boom, you can actually go and do a series of transformations on your result set. Now, that being said, for folks listening and thinking I'm encouraging you to do things like filter on a result set, please do not take that out of this discussion in this example, because if you're using especially a relational database, if there are built-in filter operations in that relational database library that you can invoke through your query that you're passing in through whatever Haskell wrapper around that relational library, I would prefer you use those built-in operations, just because the projections will be a lot faster and it will be spatially efficient once it comes into your Haskell application. All right. That I cannot stress that enough. But once you have a series of in-memory stuff, if you're using, like, say, a SQLite database or some in-memory database that's written in Haskell, and that result set is written using, or that restriction is written, has a applicative instance defined against it, you can use these transformations in that application. So that's just one idea that you can end up trying out. So that's it for this discussion. We've kind of finished up our discussions for applicatives. Again, folks watching, folks looking at this, and as with all of our algebras, discussion that we've done thus far. And I know I've said it before earlier in the discussion. I'm just repeating myself just because this is something that's often forgotten. Type class instance definitions are not formally type checked by the Haskell type checker. Please use quickcheck in the properties against quickcheck to verify your type class instances as you define them for your user defined types. Okay. If there's anything that you take away from our discussions of these, and this is something that I'm learning through this book, honestly, is especially for monoids, semigroups, functors, applicatives, and monads, and even some of the other type class instances that may have formal properties defined against them. You must provide a series of randomized property-based tests to ensure that those properties are preserved. Okay, so we have a comment here. The function lifted does not need to worry once defined about the structure of its object structure. That is correct. The value structure that my apologies for folks. We had a small hiccup there. So we had a comment about asking about the lifting of the function, not needing to worry about once it's defined the structure of its object structure. I'm assuming you're talking about when you call pure on a function before applying it to some functorial structure, as soon as it's been lifted, the function internally does not need to worry about the internals of the functorial structure. If I understood your comment, yes, you're right. You can be completely ignorant of the functorial structure once it's been lifted, and the function is just going to apply as is. It's going to be normal function application.
Okay, basically, what I'm going for is if we have some function and then we define an applicative for it, for instance, on a list, right? So as long as we have the function defined to correctly operate on the elements of the list, right, and we define basically an interface to list for that applicative function, then we don't need to care, right? And then similarly, we can take exactly.
So you're looking at it the opposite way. You don't need to define a applicative instance on the function. You're applying the applicative instance on the list. Okay,
well, let's take that. Our two pretty simple cases are just a list, right? So a one-dimensional list, and then we have a two-dimensional tree, right? And all they are is integers, and the function is +1, right? So we need to come up with some way to lift that function +1, and then also lift the structure, which is either a list or a tree, right? But the efficiency it looks like is gained is we can separate the lifting of the function from lifting the structure that the function will be applied to. So we need to come up with a way to.
So is the structure that the function is applying to a data structure that has applicative defined for it? Is it or are you saying that the structure is residing in another structure that has it's contained in another structure that has applicative defined against it? So there's two different cases here, right?
List does, right? List probably has applicative. Just take every element of this list and apply whatever.
Exactly. That's exactly why I was mentioning it. So
So then we come up with some arbitrary tree structure, and a really basic one is just the AB tree, and so then
you're right.
Right. So then we have okay, fine. As long as we have like a homogeneous, we assume, right, or we define, we make sure that all the elements in the tree are all the values in the structure of the tree are of some type that
Right.
function knows how to deal with, right?
Right.
So,
And yes, you're right. In that case, if you're defining a container structure or some structure that you want to preserve, all you have to do is, in that case, you don't even have to touch the functions. You just need to define the applicative on that structure,
right.
and
So,
pure
yeah.
will take care of the rest for you.
Right. So it'd be something like, on a tree, a binary tree, it'd be, okay, the new tree is, um, the function applied to the value of the parent, and then the left child will be the function applied to the substructure on the left, and on the right will be the function applied to the structure on the right. And
Right.
so that, so say that we want to do something like, we have a function that takes numbers and then returns their ASCII letter character equivalent, right?
Okay.
So, okay, fine, right? So I define the function, give me an integer, I'll give you back a character, right?
Right.
And then we define, okay, for this structure, right, applying this applicative means that you give me something where the parent is the function applied to the integer at the parent node, and then also on the left it'll be the recursive call on the left substructure, and then the right will be the recursive call on the right.
Right.
Yeah.
That's exactly right. That's essentially it's the same thing with functor. Right. The same rules that apply to functor will apply here. The one main thing here that you need to recognize is it's getting is that pure lifting function is doing all the magic for you for the function application, right? Before anything happens, pure make sure that both of them are functors, functorial structures to apply against each other. All right.
Okay.
And then it'll take care of the rest. Apply will take care of the rest.
Okay, but then I think a step forward with applicatives, rather than just straight functors, is that we could have some structure that defines a number of functions.
Yes.
Right, or a structure of functions that then get applied. So we could end up with, like, okay, I want 7 things done to this tree, right?
Right, and that's the beauty of that. Yeah, because of how composition works, because we're preserving composition. And again, this is another property of coming from the functor space, which is why I'm kind of sticking with functors for the time being. All right. You can take any series of functions if you want to apply to each value in your structure, and as long as you lift all of them up, all right, they're going to be applied right to left in the order in which they've been defined, right to left, not left.
Let me try putting it a little different way and see if this helps or hinders. Right. So say we have some, the thing on the left. The first thing we're going to pure is some list of functions.
Okay.
Right. So
we
it
don't
could
even
be
need to do a pure on a list of functions. The list of functions already pure, right?
Okay, fair enough.
So if you're doing pure +1 applied to pure +2, okay? Just a simple example here, right? And at the end, you are just talking about just 1, all right?
Let's say I have some suite of functions that I need to run against a tree, right? Okay. So I want to know, like, okay, give me the ID of them all. So just pass me back the same. So let's say that I have a list of functions that I want to apply, and then some set. In this case, it's going to be something that I want to apply all those functions to, right? So for instance, I want to say, give me back the identity, right, of whatever element. And then the next thing is I want you to do is give me back the ASCII value of it. And the next thing I want you to do is give me back the capitalized version of that character. So, I might get, 57 or whatever, and then little a, and then big A, right? So what I end up with doing by kind of doing the applicative of some structure of functions to some structure of objects is the structure on the left side, the structure from the left side, each element of which is the structure on the right side. So if I have some tree of 17 numbers, then and I have 3 functions, which are ID, ASCII, and capital ASCII, then I will end up getting back. So since my functions that I'm applying are in a list structure, and the object that they're applying to is in a tree structure, what I'll end up getting back is a list of trees. So the list will
let's
be.
try that. I think you're that's an important thing to check out. You're basically saying, let's say that we have just one, we have a maybe type here. Mm-hmm. You want to do this, right? Let's say that we want to double it, and then add 1. All right. Simple example. Okay.
Sure.
And we're applying it on the maybe. If I'm not mistaken, this will throw an error. Yes.
Okay.
This will throw an error. And the reason why is because the important thing about applicative is, and this is the same thing with monads. You can't mix monads, all right, necessarily. You need to exit out of one monad and then so I'm jumping ahead, folks who are watching, but this, you will end up recognizing this is going to apply the same with monads, okay? But you cannot actually go from, there are 2 different types here, right? The maybe here is not preserving the list here, and there's no type conversion between the list and the maybe, right? And
okay, but let's say we define foo, well, not foo, let's use some new ones. Cromwell as a list of functions, +1, +2, +3, right? Okay. And then we'll define, I don't know, Mao as a tree. Oh, well, let's start easy with a list, right? The list will be like 10, 20, 30, right? And then we apply, we want to apply each of the functions in Cromwell to each of the to Mao.
Yes.
Right. So we should end up with, given that Cromwell is a list of functions, we should end up with a list as a result. Yes. And each of the elements of that list will be the application of one of the elements of Cromwell to Mao.
Yes, that's correct.
Okay.
That's correct.
That's like the step up from just straight FMAP to applicative, right?
Right. That is the step. That is actually the succession, right?
Right.
Obviously, FMAP allows you to do a single function.
Right.
Applicative is now saying, you know what? What you're asking for is every function in this list to be applied to the same data set. Now, the difference being, compared to what we're seeing in the case of composition, it isn't actually just concatenating those 2 and lifting. So like, let's try this. Because the beauty, what you're seeing here, the reduction, the append, is coming from the monoidal side of things, right? mappend is being called on every result from fmap and putting them together. All right. If we
okay, okay. So wait a minute. So now we're not ending up with a list of structures that are the same structure as Mao. We're ending up with some concatenated structure.
We are.
Okay.
Well, so what happens is first we call fmap function in the one function from the list.
Mm-hmm.
On Mao.
And then kind of store it, right?
All right. And we have now a resulting list of these, okay? And we call fmap on each of these, all right? Mm-hmm. So now that results in what? A list of lists, right?
Yeah, but what if I want to kind of, okay, I mean, I'm just thinking of, where would this be a really useful thing to do? And I could think of, you have some really huge data set, right? That's, and I'm just going to say a tree structure to keep it from being a simple list, right? And then I want to run a number of operations against the data. So say I've got all these, little robots running around the solar system, whatever, and they're taking measurements. And I want to know a bunch of things that are implied by the results that I got back from their measurements. I have some crazy tree structure, yes. And I want to know a number of things about it. Like, okay, what's the mass that's detected? What's the what's the wavelength of the photon that came off of it, and what's the density? How many photons do we get in the first second or whatever? So I have this data structure, which is nothing but sensor readings, but I just want to make it very clear that what I don't want is to have a list of sensor readings and then transformations of those sensor readings into some meaningful result, and then the concatenation of things that might be something like add one and then categorize it into some visible color and then tell me the mass or whatever. So each of those results should just be of the same structure as the sensor readings. So are you saying that basically probably best to do? I mean, I thought the whole point of applicatives.
What you're talking about, you would have to use the composition operator. What I'm doing here, where you're applying a series of transformations in the order in which it's received.
Sure, but what I want
apply what normal apply, because the reason why normal apply has its defined cannot do that. It can. Well, let me rephrase that. The reason normal apply, at least as it pertains to lists, it cannot do that, is because the definition of apply,
okay,
is
so that's why you
essentially defined as an F map with an append. All right. And
okay.
I'm using the monoidal M append definition along with the F map from functors. Okay. So we're preserving the functor piece, and then we are defining how they should kind of concatenate with each other, right? So to preserve the monoidal structure, the monoidal property of the apply.
Okay, that makes sense. So I'm going to have to get back as the final result some structure that is of the same shape or meta shape as the input on the right side.
Yes.
So I have some list of functions or some structure of functions, and I have to end up with something that is of the shape of whatever I passed in on the right. Okay, that's interesting. So then,
because that's a structure preserving property, right? That's
okay. I got it.
Talking about structure preservation, you're talking about it.
You're right. I totally get it. So if I did, I mean, let's just say that we have this two-dimensional tree of sensor data, right? I don't know what the two dimensions are, like time and location and space or whatever. But then, I then end up analyzing these in 17 ways. So now I want a 2D tree, but then I want 17 layers of that. So then apparently what I should do is do fmap on that tree, and then have some loop structure that would just say, okay, do it each of these times, and then append those together. And now what I'm getting back is a structure that is top level. It's the same structure as what's on the left, but then each element of which is the structure on the right.
Right.
Yeah. Okay.
At least that's how I understand it. Right.
We'll just say simple picture. Like we have 7 elements in a tree. Those are the 7 readings that we got from our thing to going to Mars or whatever. And then I have 17 ways to analyze those readouts.
Right.
So now I have a list of 17 functions, each of which I want to map over the tree of 17 or whatever 7 sensor readouts, right? And then I'm going to end up with my vision is a bunch of little glass slides, like from the good old days, right? So each slide,
you're basically saying for each value in the 7 sensors, you would have in the resulting list a glob, if you will, right?
Sure.
That represents that specific sensor reading applied to every one of the 17. Well, taken as every one of the 17 functions and connected together into a single structure. So for each value, all 17 transformations.
Right. So the structure of the functions in the easy case is just a list, right?
Right. And that's a slightly different. That's not what would happen in the case of list, as you can see right here, right?
Mm-hmm.
What's happening
I know,
is
it got
it'll
flattened,
take,
basically, right?
yeah, it got flattened. Well, it's not even just that it got flattened. It didn't even know that 10 was applied to 11 here, and then 10 was applied to +1 here, +2 here, and +3 here. It has no way of knowing that, right? You would
Okay,
have
so
to figure out a way in,
I'm looking for something kind of in between, right?
yes.
So what this is doing is giving me back something in a structure that is the same structured type of
Right.
the right-hand side, right? So I've got some functions over on the left, and then I've got some data structure on the right, and I'm going to end up with a data structure that is of the type of the right-hand thing.
Right.
So what I'm saying is, okay, I have, in the easy case, a list of 3 functions that I want to apply to a bunch of sensor readings, and all I have is a binary tree that has 8 elements, but it's a tree.
I know what
right?
you're asking for. Given these 2 examples, you're looking for something equivalent to where you get 11, 12, 13. The first one, 21, 22, 23 in the second one, and 31, 32, 33 in the third
Not quite,
one,
right? No. So what I'm doing is, my list of functions, let's just say it's +1 times 10 times 100, right? Those are the things on the left-hand side, a structure of functions to be applied. And then on the right-hand side is, in the easy case, some list of, like, 4 sensor readings or something like that. 1,
It
2,
doesn't
3,
matter.
4.
We have 10, 20, 30 here in this example, right?
Fair enough. But then the structure that I want back would be a list of the same order and size of the functions that got applied. And each of the elements of that list would be of the structure of the sensor readings that I got on the right-hand side, right? So if I have basically, I want some way to iterate a bunch of functions that are captured in some structure across values that are captured in some other structure, and I want a list. So in the case where the functions are in a list structure, +1 times 10 times 100, and then the data in this, just to keep it easy, it happens to also be in a list, and it's 1, 2, and 3, right?
Okay.
So then what I want back is a list that has 3 elements, and each of the elements is the application of one of the functions on the left-hand side to all of the elements on the right-hand side, returning a structure like the right-hand side, but then kind of wrapped around.
You just want in this case 11, 21, 31.
Yes, something like that.
Yeah, so you want the list of lists. You don't want it to be concatenated.
Well, I want the structure of structures, right?
Yeah,
so,
or structure of structures. It doesn't necessarily.
Correct. That's kind of what I'm looking for, right? So what would that be? Do I have to do that by hand, or is there some?
So that
tool?
right now, I don't know if the apply is the one that you'd want to use. I think you would have to use
like map.
I don't know,
right?
maybe fmap over.
Yeah. Okay. Fair enough. Right.
Yeah.
Maybe I'll go back and read some more, but
yeah, I'm pretty sure you'd have to use fmap because, again, what you're asking violates the not the structural preservation property, the composition property.
I think it's composition. Well, yeah, because we're not coming back with if the right-hand structure is, for instance, a tree.
It's composition because it has to apply to this first and then apply to this second.
Right.
And then internally, this function here is actually applying and then concatenating. Again, the definition for applicative for applications specifically is fmap over
Okay. I mean, I'll think about it, and I'm sure somebody's done it, right? So it,
Yeah.
it seems kind of straightforward, right? So you got some structure of functions on the left-hand side, which will define the top-level structure of your results, and then you have the structure that you're applying them to, which will determine the structure of each of the elements in the return structure, right?
Right.
Okay, fair enough. Anyway,
Okay.
great class, man. This is really interesting.
Okay. Cool.
I'm looking-
Um, so uh, tune in next week when we actually hit the meat of our discussion,
Oh no.
the culmination of our journey into the big kahuna of what Haskell seems to be the rave about, which is monads. We'll be talking about monads and at least getting started on our monadic journey. No pun intended. I'll see you guys next.